good. So let me write the point where the thing that I did last time, which was the superspace action for charged matter superfields coupled to an Abelian gauge superfield or vector superfield, and it looked like this. I'll write it across the board, and then below it we'll write down in components what this thing looks like. So this plus 1/4 integral theta So I hope you haven't forgotten all this notation. Phi is a chiral superfield. The index I runs over any number of such fields. V is a vector superfield. WA is derived from V by writing this. It has three supercovariant derivatives acting on V. V is not gauge invariant. V transforms like this, while lambda is a chiral superfield that represents the gauge parameter of U1 gauge transformations. And under this transformation, the matter fields, the matter superfield phi transforms as phi I goes to the minus 2ig ti lambda and this pair of transformations is the U1 gauge transformation in superspace. Obvious that if I take the dagger of phi, which will be an anti-chiral superfield, it will transform by a similar phase but involving lambda dagger, which is the anti-chiral super gauge transformation parameter. All clear so far? Okay. Now we would like to take that Lagrangian up there and expand it so that we know what it looks like in ordinary component fields. Thereby we learn what a supersymmetric gauge theory looks like. That's the building block of the standard model. It's still Abelian. In a few minutes I'll switch to the non-Abelian case. But before that, let me point out to you that there's one, and essentially only one type of term that I missed writing when I wrote all this, and I'll write it now. It's rather a curious term. It's a curiosity of supersymmetry, and a very important one, of course. Curiosity, I mean in the theoretical sense. In practical sense, it will be very useful. And it consists of saying, let me put an arbitrary numerical constant eta and integrate just the vector superfield itself. Just take its last component. Okay, so it's a linear term in V. Right? You remember that the vector superfield had an auxiliary field at the end of it, the last term, theta dagger, that was called V. Okay, that was called, T. The auxiliary field of the vector superfield is called D, and so this integral just produces D. So this term is eta times D. Okay. Now D is going to be an auxiliary field. So from elsewhere in this system there will be a term like D squared, and there will be some linear coupling of D to something else, to some other fields. And here we have a term eta D, and it's going to be quite non-trivial. Okay, it looks pretty harmless, but it's non-trivial, and so much so that it goes by a name. It's called the phi Heliopolis. D term. I pointed out to you that D occurs all over the place. It always means the last component of any vector superfield. So you could use the name D for the last component of this complicated vector superfield. Okay, but here it's the fundamental auxiliary field occurring in the last component of the vector superfield, which contains a U1 gauge field. And we'll see that when there are many U1 gauge fields in the theory, then there will be many D terms. Yes.
We have a surface term which goes like epsilon mu lambda sigma mu
Lambda sigma mu.
Basically E dot B term.
Okay.
So that term, how would we get it?
Sorry, I got confused by lambda and sigma. What are lambda and sigma?
Okay, those are the indices.
Oh, I see. Sorry. So say it again.
Epsilon mu lambda sigma, F mu lambda sigma.
F. Okay, good. So the term you're talking about is the term that we call FF delta.
Yeah.
Yes, that's correct.
So that term, if you want to get it in Lagrangian, how
yes.
do you get it through this method?
Yeah. Thank you. That's a good question. We shouldn't really worry about it in an Abelian gauge theory where it doesn't do anything. In a non-Abelian gauge theory, it will do something. So let's come back to that when we do non-Abelian gauge theory. That is an important question. Okay. Good. So now I will write down for you the answer that you get when you take all these superfields, plug them into these three type of terms, and then integrate out theta and theta dagger, which you can always do. So who's already done this over the weekend? How many people have ever done any calculation pertaining to this course? Okay, let me ask the question another way. How many people here have never done any calculation pertaining to this course? Very good. Okay. And okay, so I'll do all the work, but unfortunately I'll be the only one to end up learning in that case. Okay. So I'm going to start writing all the terms, and then we'll do a little in-class quiz where we'll try to identify from which of these three terms each of these comes. Okay, you can already start working on it while I write. So the quiz will conduct as follows. Let this term be called 1, this be called 2, this be called 3. As you can see, they are all in some sense independent of each other. They have different forms. So now you have to look at every term in this and tell me right away whether it comes from 1, 2 or 3. That's the only possibility. So this comes from 2. Very good. Who said 2? Okay, good. This comes from 4 actually, which I didn't give a name. Okay, this from 2, 1. Very good. 1. Okay, now somebody who hasn't answered yet. This from this region, anyone has an opinion? minute to wait, however long it takes. You don't need to look up your notes. If you're following the course, it's all on the blackboard what you need. I want to know where F star comes from in this thing.
What is F5?
It's the auxiliary field in phi, right? No. It can't come from 3y because it's the field times its own complex conjugate.
So it's when
It comes from 1. It's just the last term in this times the last term in this. Okay. Phi terminates in theta theta f. This terminates in theta dagger f star. After doing the integral to get f star. Okay. This comes from 3. Very good. We're getting there. This one. Also from 3 has w, no? This the curly w is only in 3. Okay. Now we get to two interesting terms. This one comes from 1 because okay, very good. That's correct because it contains Ti. In fact, can you read it off right away? How it comes? Let's do it for you. Phi is the first component of this guy. Okay. Lambda is the third component of the third order, that is theta dagger. So there are 3 thetas there when I expand this to first order in V. And then psi is the theta component of phi. In fact, the theta dagger component. Okay. So from this one, if this one comes with theta dagger, this comes with the theta dagger. The integral eats up all the thetas and you're left with this. This is a very important coupling. That's a hallmark of supersymmetry. And just to give things a name, I'm not sure if I gave these names last time. If phi is a scalar, if psi is a conventional fermion that exists in the standard model, okay, where psi is a fermion that comes in a chiral superfield. So this could be the, I'll develop this thing later, this could be the electron or a quark or something, more generally a fermion. We use, of course, lambda is also a fermion, but we have a special name for it. Lambda is the fermion in the gauge multiplet, so it's called a gaugino. It's the fermion partner of the gauge field, and it appears in the vector superfield. Okay, and this guy is the scalar partner of a fermion, so it's called a fermion. If this was an electron, this would be a electron. If this was a quark, this would be a quark. So we have a coupling fermion gaugino. This is a hallmark of supersymmetry. Of course, you could say that's a silly statement because the very existence of fermion and gaugino is a hallmark of supersymmetry. But in those models, not only do we predict these extra fields, but we predict a very precise trilinear coupling between them. Okay, it's a Yukawa coupling involving 2 types of fermions, the gaugino and the matter fermion, and then this fermion. Notice that if this fermion being a scalar, if it ever gets a wave, this will be a mass term linking the gaugino to a fermion, which means there will be mixing between gauginos and matter fermions. Okay, is that point clear? One kind of fermion that comes in a chiral multiplet, another kind of fermion comes in a vector multiplet. The two will mix if the scalar in the chiral multiplet gets a wave. There will be a mass matrix. There could be many other mass terms. Where would they come from in this Lagrangian if we had other fermion mass terms? This term. Because W can have a quadratic piece, then this is a fermion mass term. This is a fermion gaugino mass term. You would have to diagonalize the whole business again. Okay. Can there be a gaugino direct mass term?
Not necessarily the mass of the bosons.
That's right. Since the gauge field is massless, mu has to be massless by gauge invariance. So the gaugino has to be massless in this Lagrangian. But at the end of the day, if there's this mixing, then what we call the gaugino will not be an eigenstate or mass, and we'll have some other particle which can be massive. So we should be prepared for some complicated business to happen. Okay. And here's another hallmark. There's a coupling between the auxiliary field D and the fields phi I squared. These are the fermions. and the strength of the coupling is proportional to the charge of these fields. Remember that Ti is the electric charge in units of G, which is the quantum of electric charge. So if you like, this is the total electric charge. This also comes here. So both this Yukawa and this coupling to the auxiliary field occur with strength proportional to the electric charge. In particular, if there are any neutral chiral fields in the theory, which there might well be, then they won't have any couplings. And this all clear? Okay. Now, what's the next thing we should do in order to get a feel for the physics of this? Integrate out the auxiliary fields. That's what you said. Okay, thank you. So can you see how to do that? Pretty clear. Let's do F first. F occurs only here and here. So we find that F star I is equal to minus W comma I, and we find that D is equal to minus G T I by I squared, by the way there's a sum over I both here and here, minus theta. So you see the phi Heliopolis parameter theta making its appearance. Okay. And now when I substitute these, here's a quick recipe. When I substitute this, I'll get this term, and the complex conjugate, 3 terms. Will all be proportional to W comma I mod squared. But this one will come with a plus, while these two will come with a minus, and the net result will be minus. So eventually, we find that L equals lots of terms minus V. This is by convention T minus V. V is the potential, ordinary potential of phi and phi star, with V being equal to W comma I of phi mod squared plus a half mod of, well not mod of, eta plus GTI phi squared. It's clear what's happening, right? Again, what happens is that the theta, when we eliminate t, this will be half t squared. The rest of it will give me minus t squared, where t has been substituted by its value from here. Maybe I didn't say that right, but at the end of it, you get defining L to be all these terms minus V of phi and phi star. The potential V of phi star is the sum of these terms, and we notice that both are positive, semi-definite. They can, in principle, both be zero, but there is no guarantee that both will be zero. In fact, you can see something very interesting right away. Supposing W comma I vanishes at phi equals 0, which is more than possible. For example, if it's just a mass term, it will vanish. If W is a mass term, then this is linear in phi, so this will vanish at the origin in field space. So will this. So we see that the potential is bounded below by a positive quantity, half eta squared, where eta is the phi Heliopolis parameter. So we can bound the potential below by anything we like, just by putting in this parameter in the Lagrangian by hand. Okay. However, of course, W may also have a more complicated form, and so the general way to figure out how the potential looks is to write out the entire potential. This is both contributions. This is called the F term contribution to the potential, and this is called the D term. That's obvious because they were obtained by solving for the auxiliary fields F and D respectively. Okay. One more thing which I don't need to stress, but maybe at this stage it's good to say, is that supersymmetry is clearly telling me that a wide variety of potentials are allowed, but not anything I like. Okay. It's not in the least obvious that if I dreamed up some potential, I would be able to write it as one of these terms or as the sum of these two terms. Okay. So it limits my choices, which is good. And with that, okay, the last exercise we have to do, and this is extremely useful and will take us close to the standard model. So last exercise before we get to non-Abelian gauge geometry in supersymmetric theories is to write down the Lagrangian for supersymmetric QED. So what is supersymmetric QED? I'll keep this top line up there as a kind of guide. Of course, it's slightly absurd to say QED. I should have said CED, classical electrodynamics, because we are not doing quantum field theory as yet. We've been doing nothing but classical field theory. But okay, the Lagrangian, which you will quantize in order to get the supersymmetric generalization of QED. This will make us think that given fields which we already know to exist, what do we need to extend them to, and how, in order to have supersymmetry. Okay, it's in some sense a trivial extension of this, in which we'll have to commit to how many chiral superfields we introduce and what their content is. And we'll learn a very important lesson from that. So what do we want it to have? Well, we certainly want QED to have a gauge field, the photon. And we need it to have, let's just say that for the moment, we'll take the definition of QED to be the theory of photons and electrons only. No quarks. Okay, and no muons or anything else. So if we have electrons, of course we have the following electrons: the left-handed electron, the right-handed electron, the left-handed positron, and the right-handed positron, where this is the same as E right dagger, and this is the same as E left dagger. Okay. The charge of E left and E right in my conventions is +1 in units of electron charge. So there will be a unit of electron charge floating around, which is minus some number. I find this notation a bit confusing, but from the day that people found the electric charge of the electron to be negative, that convention was set. And once we decide that this is +1 in those units, then of course these are -1, which agrees with the fact that they are the complex conjugates of those. Okay. Now that's the content of ordinary QED. On the super side, let's ask what do we expect. So A mu, the photon, must be embedded in a vector multiplet. Okay, so that means that there's going to be a lambda, which is its partner, which will be called the 14, consistent with these conventions, naming conventions. So photon. Okay, and then we are going to have scalars, which will be called selectrons. They are S fermions. Okay, so that's because. Okay, so why is that? Well, these are fermions, so they have a choice. They could either be appearing in a vector multiplet or a scalar multiplet or a chiral multiplet. But if they occur in a vector multiplet, then there will be more gauge fields in the problem, and we just want one gauge field in QED. So they should occur in a chiral multiplet. Okay, if they occur in a chiral multiplet, then there has to be some number of scalars phi, which are their scalar partners. How many exactly, we'll see in a moment. Okay, so there's nothing much to say about the vector multiplet because there is just one real vector superfield. It contains lambda in the cubic place, this in the quadratic place in theta, auxiliary field in the last place, but that will take care of itself, so we don't have to write it. And the fields in the first and second and third places will be zero in the West Zubino gauge. Excellent. Okay. So that takes care of this. So we must have a vector superfield B. And what's little less obvious is what we expect in terms of scalar superfields, of chiral superfields. So let's start with one, which is going to have a complex scalar in the first place. And then I'm going to require that over here it has the left-handed electron. Okay, I won't write the auxiliary field, but it's just there. Now, if I take this and I dagger it, I'll get an anti-chiral superfield. That's not an independent quantity. Once I postulated a chiral superfield, then its anti-chiral one is always there, and that one will contain what? Yes, and EL dagger is the right-handed positron. Okay, so what have we not obtained in this chiral superfield? ER and PM. Okay, So that means we need to introduce another chiral superfield. So therefore let me call this one phi plus, and I'll write it like this. And note that the auxiliary field will also have the index F plus. If you like, this would also have the index plus. Plus by our convention is the electron charge in the charge of the electron in units of some number q. In those units it's plus 1. This I won't put a plus because instead I want you to see explicitly that it's a left-handed electron. Okay. Now the next chiral superfield, before I even start writing it, I need to decide what occurs over here, and I have two choices. It can either be ER or PL. Which one do you think it should be? Okay, so
but the index structure will determine it, right? Because ER will transform, like will have a dotted index.
Very good.
But theta has has an undotted index. So we can't contact it with anything.
Actually, that's the same thing as what you were saying. Because exactly. These are undotted. In fact, this is the reason why this notation can be confusing, because when you see it in this form, you are not sure whether these are dotted or undotted. They have a dagger also. In this notation, it's crystal clear. All left guys are undotted, all right guys are dotted. Okay? Therefore, we in fact have no choice but to put PL over here. And from now on, we remember the important lesson that a chiral superfield always contains a left-handed fermion. Okay, this is the rule. That's in fact the best explanation why the word chiral was ever given, which we never explained. And it's the same as what you just said, theta in fact, so I was actually about to disagree with you and I was wrong. Theta in fact is left-handed and theta dagger is right-handed. Okay, and that's because the SL2C Lorentz group splits into a left and right-handed part, which are the two SQ2 factors. So that's this. From this we can read out the fact that this has a negative charge. Okay, had it been allowed to contain ER, it would have had a positive charge in those units, but this clearly has a negative charge, so it deserves the name phi minus, and its first term is called phi sub minus. It's a scalar field, but it's not the complex conjugate of that. Complex conjugate of this is another negatively charged field, and this is a different negatively charged field. Is that part clear? If I complex conjugate either of these, I don't get the other one. I get anti-chiral superfields containing phi plus star and phi minus star, which have the opposite charges from phi plus and phi minus. Okay. So we see that there is an interplay between supersymmetry and charge, if you like to put it that way, which requires two separate chiral superfields. To accommodate the fermions, the matter fermions. Okay, and this will be a hallmark of all the theories we develop. And now you can see for yourself that if I were doing the standard model, we know that the left-handed electron is in a doublet, the right-handed electron is a singlet. That means that the left-handed positron is in a singlet. Is that clear? And therefore this would have been a doublet and that would have been a singlet. So we see how the left and right-handed pieces, the chirally asymmetric pieces of the standard model, when we embed them in supersymmetry, then we'll have some chiral superfields which are doublet and others which are singlet. The ones which are doublet will contain the left-handed particles, the ones which are singlet will contain the left-handed antiparticles, which are dual to which are CPT conjugates of the right-handed particles. Okay, very good. And now, there's not much left to do. We just copy this prescription for this set of fields. We just notice that there are these two fields. So the only things to point out in SQED are the following. The only things that are surprises or that are noteworthy. First of all, W equals M phi plus phi minus is a mass term. It's clearly U1 gauge invariant because if phi minus transforms by a certain phase given by its charge, phi plus transforms by the opposite phase. Okay, so it's phi plus phi minus. And so it's charge neutral or gauge invariant, which is the same thing. And if we translate this into ordinary space, we'll get MELPL plus EL dagger, which is exactly what you expect. So this is how the mass term originates. Okay. For the same thing will also give me masses for the scalars, but the pattern for scalar masses is quite different. It's not phi plus times phi minus, but instead phi plus times phi plus star. This happens from the auxiliary field structure. That miraculously this term induces both this and minus m squared, phi plus star, phi plus phi minus star, phi minus.
M square.
Sorry?
How will m square come?
You tell me. We've done this already. How will m square come? No. Sorry?
It comes from two terms.
What two terms?
One is the m phi auxiliary times phi.
Very good.
And there is another
Which auxiliary field?
d.
No, not D. F. F times m phi and f squared.
Yes.
If we combine those and integrate out f, we get m squared phi squared. Not only that, it's that clever combination, it's that fact which allows us to finally get phi plus star phi plus. You should be very surprised by this because this is a coupling between scalar fields in a chiral and anti-chiral superfield. When we started by putting the product of two chiral superfields only, plus the product of the complex conjugate which involved the two anti-chiral superfields. Okay, so the presence of auxiliary fields in this theory is crucial to reproduce this kind of structure. So this is very important to note. So this is one noteworthy fact. The second noteworthy fact is that we saw that we have some couplings that are proportional to charge, and they were the trilinear or Yukawa coupling, which turns out to be √2q lambda dagger E. So now I'm working in a basis which is commonly used where we never refer to the right-handed particles by their own name. We only refer to EL, PL and EL dagger, PL dagger. Lambda dagger into EL dagger phi plus minus PL dagger phi minus plus lambda into EL phi plus star minus PL phi minus star. So what is going on here? This is what I call the fermion gaugino coupling. This is the gaugino, lambda and lambda dagger. These are the actual electrons and positrons, and these phi's, which you see all four of them occur, phi plus, phi minus, phi plus star and phi minus star, are the fermions, in this case the selectrons. Okay, and the couplings are all proportional to Q. That's because up to a sign, Q is the charge of E's and P's. So there is this. Moreover, notice that this sign is important. It occurs in these places. And also notice that although I have written it in this way the charge neutrality is manifest because this has a negative and this has a positive charge, this has a positive, this has a negative charge, and so on. Okay, you should check that. On the other hand, the fermion indices are contracted between lambda and E, lambda and P, lambda and E, lambda and P. You notice that lambda dagger occurs with E dagger, P dagger, and lambda occurs with EL and PL. So that here they are dotted indices, and in this line they are undotted. Okay, so all are things to notice. The third observation is there's another term proportional to electric charge, which is the term contribution, and now I forget what I wrote earlier, so there should have been a square somewhere in that story, and I'm not sure if I wrote the square correctly. I think. It was g times di phi I squared times d, but when I integrate out d, then again I get the square. And so it's q squared by 2, and then I have phi plus star phi plus minus phi minus star phi minus squared. Again, a characteristic signature of supersymmetry. I told you that the d term couples with a charge ti. Okay, sorry, the d term couples with a charge proportional to the charge and phi star phi, where phi is the field in a chiral superfield. Okay, so notice the amusing thing here. This term has come with a plus because phi plus has a charge plus 1. Phi plus star has a charge minus 1, but the term comes with a plus because this is the one in the chiral superfield. This is in an anti-chiral superfield. Of course, the overall interchange of the two wouldn't matter because everything is inside a square. Okay, but you see that the relative sign of this chiral superfield and this one, that is this phi plus and this phi minus, is minus. Okay, and when you have four different scalar fields and you have a potential involving a minus, you see that there are lots of interesting possibilities. For example, to make this whole potential 0, all we need to do is put the mod of phi plus equal to the mod of phi minus, which is a lot of solutions, and they'll all minimize. So there's a whole family of solutions to minimize this. Okay, wherever mod of phi plus is equal to mod of phi minus. Okay, so that characteristic sign occurs because of that structure summation ti phi I squared, which couples to the d term. So I hope that from this you are getting some conceptual idea how supersymmetry constrains Lagrangians, and not just the technical idea that you have to do lots of theta integrals and get whatever you get. So these are sort of more universal facts. Good. So that concludes our discussion of Abelian gauge theory, and now I'll go to non-Abelian gauge theory. Are there any questions? Everything? Now, if you put yourself in the position of people in 1970s who had understood, let's say, all that we have done by now, namely chiral superfields, vector superfields, and how to couple them in the Abelian context, and we imagine them asking, how do we extend this to non-Abelian gauge symmetry? It's almost of the same type of question that Yang and Mills asked in 1954, because there they were given Abelian gauge theory, and they asked how to make non-Abelian gauge theory. Here you are given Abelian gauge theory in superfields, and now you are asked to invent non-Abelian gauge theory in superfields. Okay, so it's a almost equally exciting enterprise. Some aspects of it are completely obvious, and then many aspects are quite non-obvious and very striking. So the obvious thing is that we should extend A mu to a bunch of gauge fields A mu with an index A, where A runs over the dimension of a group. I use the word group because physicists use it. Really, it's algebra, not the group that we use most of the time. And the dimension of the group, the only groups we'll ever be really bothered with are SU2 and SU3, and the dimensions are 3 and 8 respectively. So that's what that index is. Okay. And the only way this can happen is that in supersymmetry, we generalize the vector superfield to be a multiplet of vector superfields VA of x, theta, and theta dagger, with A going from 1 to 10G. So that part is pretty obvious, because in the middle place of VA, when we expand it out, there will be a theta sigma mu theta dagger multiplying A mu A, and so we'll get that number of gauge fields. We'll also have a number of gauge transformations which we'll anticipate will set to 0 the first few components of the vector superfields, and after the gauge field, hopefully we'll get a gaugino with the same index A, and very, very important, a D term dA. So you get a bunch of beta of T auxiliary fields in this superfield. Okay. Now let's introduce the generators satisfying TA, TB is I, FA, BC, DC, emission generators. Okay. We should also fix the normalization, which I am following the textbook of DGR, which fixes it to be like this. So the point is, of course, this doesn't uniquely fix the T's. They can have any dimension as long as that dimension is the dimension of some representation of the algebra. Okay. Most commonly, in the case of SU2, these can be 2 by 2 matrices, then they are Pauli matrices, or they can be 3 by 3 matrices, then they are the epsilons and they give the adjoint representation, or they can be higher dimensional. And similarly for SU3, they could be 3 by 3, that's the fundamental, or they could be 8 by 8, that's the adjoint, and there can be lots of other things. Okay. So T is a characteristic number associated to the representation, but we leave it free so that our formulae will hopefully be independent of this choice of normalization. Clearly we can multiply all the T's by any number we like at the cost of changing the value of S by a factor. So this, once we know the T of R, then we know the normalization. Okay. Now there's a subtle, well, we've already seen it, the subtle factor of 2 which keeps occurring in this story, which leads us to define B. This tilde underneath means it's a matrix. I'm not writing the matrix, and so these are all okay. So we'll define a matrix valued B to be twice the coupling strength G that we desire for the non-abelian gauge group, summation of BA times the generators T. So therefore this matrix valued B will be the same dimension as any particular representation we have chosen. If you look back in your notes, you'll find really that the factor of 2 already occurred, because when we did gauge transformations, we found that in terms of the gauge parameter alpha, the gauge transformation was A mu goes to A mu minus twice del mu of im alpha. By the way, I believe now that there was a sign problem there. It should be plus, I believe. If any of you cares, the few of you who care should go back and check your notes. I also think there's a corresponding error in DGR, which will be useful if you find it, because we'll tell it to them. So the minus I had last time should be a plus, but anyway, the normal parameter beta, under which A mu goes to A mu plus d mu of beta, is related by a factor of 2 to im alpha, and that's the factor of 2 which keeps propagating here. Okay. Now, what we want, okay, so here let me just say one more thing. This A goes from 1 to dim G, but the dimension of the matrix is dim R cross dim R, which is the dimension of the representation. I've already said that. Okay. Now, what do we want to do? Well, we want the analog, superfield analog, of delta A mu A equals d mu beta A plus G FABC A mu. This is the non-Abelian gauge transformation written in some variables. But it's actually more convenient to write this in matrix language. That transformation is A mu goes to G inverse A mu G plus G inverse D mu G I. Right, I hope this is all familiar. This G underlined is the exponential, in fact I'll write it. This G is e to the I beta A dA. And here all the matrices are defined by just taking the components like A mu A and multiplying it with dA. And maybe putting a coupling constant G. Sorry if there's any confusion, but not related to this. So this is what we know, and now we want to generalize this to superfields. And what we know for sure is that, or what we can be reasonably sure about, is that in superfields, this quantity, the group element e to the I beta ATA, will be replaced by, can someone tell me what they think it will be replaced by? What is beta replaced by? Lambda, capital lambda, the chiral superfield gauge parameter. And that factor of 2 tells me that it's really 2IG lambda A. So this I think we can be reasonably confident of, okay, that this is going to reduce to that, and more maybe other terms, but in a suitable part of this will be equivalent to that. Okay, and we can define then the matrix lambda to be 2G lambda A TA. So the group element, by group element I mean the exponentiated algebra element, which is actually an element of the V group. The group element in superspace is e to the I lambda, where lambda is simultaneously a matrix and a chiral superfield defined by this equation. Okay. Now something very interesting you can see immediately. If I dagger this, given that T is a Hermitian, I get its inverse, e to the minus I beta LTA. But if I dagger this, what do I get? E to the minus I lambda dagger. After daggering, it turns into an anti-chiral superfield. Okay, so we should be prepared for some things to be quite non-trivial once we made this leap. Okay. Now let's see let's guess what the gauge transformation of V should be like. So how should V transform? You have all the ingredients on the board. V contains an A mu. This thing is roughly G, and A mu transforms like this. So we can try to copy that and make a guess how V transforms. We'll find that the guess is wrong, the first guess is wrong, then we'll have a second guess which will be right. So the naive guess is that V goes to e to the minus I lambda dagger V plus something. Actually, this is not so bad. Okay. The problem is, it's not easy to fix up what the plus something should be. Because remember, we don't want to use ordinary V mu. Okay. And another thing we should remember is that in the Abelian case, this is all underlined, all matrices. In the Abelian case, V went to V plus I lambda minus lambda dagger, and you see that there are no derivatives in this expression. Only when we go to ordinary space, it turns into A mu goes to A mu plus del mu of beta or del mu of m alpha. But there are no derivatives in this, so we really don't know what dot 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 should mean, because we anticipate there will be no derivatives in this either. Okay. Moreover, we know that if we take the correct formula for this and specialize to the case where these matrices are 1 cross 1, which means the Abelian case, then it better reduce to this. Okay, and with all of these facts in mind, the guess, the correct answer is very easy to write down. It just requires to exponentiate V and say that e to the V goes to e to the minus I lambda dagger, e to the V, e to the I lambda. You see that if I expand this to first order and V on both sides, it's that. On the other hand, if I restrict this to abelian, then I can just add up the exponents and I get this. Okay, so restricts correctly to abelian case. Now let's see if we can, with this thing, manufacture a gauge invariant action. First, let's analyze this a little bit more. There's a very well-known theorem which tells you how to combine exponentials, Baker-Campbell-Hausdorff theorem. So you can do that, and you can solve this to find out how V transforms. Namely, combine these three things until it's finally of the form e to the matrix, and then equate that matrix to V, okay, to the transform V. And you know that in that PCH theorem, combining exponents means commutators of commutators of commutators, and it can be infinite unless for some reason things commute after some time. There's no reason on earth why these things should commute after some time. So it's going to be an infinite nonlinear thing, and the best we can do is write a few terms of it. V goes to V. The first correction must be the abelian term. The next correction turns out to be I by 2 commutator of V with lambda plus lambda rather. The next correction turns out to be I by 12 V with V with lambda minus lambda rather, and then there are infinitely many more. Okay, and the many more will contain not only higher and higher powers of V, but also higher and higher powers of lambda, because everybody here keeps commuting, so you get all kinds of higher powers. Okay, well, this doesn't look like what we want, because we would have wanted that a mu goes to a mu plus this plus one term of this sort, this containing a and this containing the gauge parameter, and then nothing more. Okay, but we can take heart from the fact that in the Wess-Zumino gauge, superfields reduce, vector superfields reduce in such a way that higher powers are zero. For example, we saw that in Wess-Zumino gauge, V cubed is 0. Okay, so that's certainly going to cut out from this in Wess-Zumino gauge all the terms involving V cubed, so that will terminate. But that's not enough. What happens is that lambda, generically a gauge transformation like this, even if you were in Wess-Zumino gauge, after this you are not going to be in that gauge anymore. Okay, unless lambda is also special. Okay, so you have to keep a lambda preserving Wess-Zumino gauge. Since my intention in this course is not to go into this level of formalism in too much detail, I'm just going to make this comment that you need to go into Wess-Zumino gauge for V, and then also restrict lambda. So choose V in this gauge, and then restrict lambda to contain only im alpha. Remember that lambda contained the real alpha and im alpha and a psi and an f. Okay, but the real part of alpha as well as psi and f in the abelian case were used up to go to Wess-Zumino gauge. So the physical gauge transformation over and above what put you in Wess-Zumino gauge involves only im alpha. So let's choose a lambda depending only on that. Okay, and then I should be able to show you that we get the correct desired answer. So let's do that. It's a very simple exercise. We find that lambda k is minus I alpha a minus I theta sigma mu theta rather del mu alpha a minus a quarter theta box of alpha A. Right? Where this I've just solved for the fact that if you remember in a previous lecture I had called the gauge transformation parameter as phi, and phi was I lambda. So if I take this minus I the other side and then I had expanded phi like this with also terms depending on psi and f. Now I put those to 0 and I am also choosing alpha to be imaginary. So alpha will be equal to I beta A over 2 where beta A are real. And with this 2, I'll be converting from the natural normalization of parameters in the superfield gauge parameter to the ordinary field ones. So in terms of this beta, my gauge transformation of A mu should come out to be A mu goes to A mu plus capital D mu of beta. Okay. So with this, it's an easy exercise to work out that lambda A minus lambda A dagger times I, which is this term, is equal to theta sigma mu theta dagger del mu of theta A, while lambda A plus lambda A dagger, which occurs here, is given as theta minus 1 for theta dagger box of beta. Okay. You see what's happened? First I replace alpha everywhere here by I beta by 2. That I will eat up this. Then when we take lambda minus lambda dagger, this term and the last term will drop out due to alpha being imaginary or beta being real, and we'll only be left with this. But when I take lambda plus lambda dagger, the opposite thing will happen. The first and last terms will stay. Okay. Now I have to plug this into this equation. So it's pretty easy, and I find that delta of A mu comes out to be del mu of beta. That's already guaranteed because here's del mu of beta, it's occurring there, plus another term which is going to be 2g. I have to go from matrix notation back to, so here I have to go back to the matrix notation by multiplying it by 2g times dA. So at the end of the day, I find 2g times I by 2 times A mu beta. And so this is D mu beta plus I g A mu beta, which is the correct translation. This is D mu beta. So we've shown that with this choice of gauge transformation on the vector superfield, that e to the v transformed in that way, and then assuming that the vector superfield has been put in Westervino gauge, as well as the gauge transformation has been restricted to keep it in Westervino gauge. When you do both of those things, then you find that the variation of A mu under gauge transformations is exactly what it is in ordinary gauge theory, ordinary non-Abelian gauge theory. In general, this would, if we are not in Westervino gauge, then this would be corrected by lots of terms, depending on the unphysical fields C, M, and whatever else we could gauge away by going to Westervino gauge. Those fields in turn will have a transformation which will involve A. It will be a very complicated system. So Westervino gauge is always the best to go into to see the physical content of gauge invariance, and then it better work out that it gives exactly what ordinary non-supersymmetric gauge theories do, and this is what they do. Is this clear? Good. Okay, now we are by no means done. We've just confirmed that this exponential transformation law of V is a correct one. Now we need to get a gauge invariant field strength. And you remember how gauge invariant field strength worked without supersymmetry. And you also remember how it works with supersymmetry in the Abelian case. So now we have to just combine. Okay, so we have to generalize WA equals minus 1 for D dagger B to the non-abelian case. And this turns out to be really a masterpiece of theoretical work. The answer is amazingly beautiful and subtle. Okay. First of all, this formula involves V directly, but in the non-abelian case, we have seen that the only variable you should ever deal with is e to the V. By the way, I forgot to say this earlier. You remember that in the previous lecture we showed that V is dimensionless. Therefore, e to the V makes perfect sense. In fact, e to the V already appeared in the abelian case, but there it appeared when we were coupling to charged fields. And here we've just said that it appears in the gauge transformation, that the rule for gauge transformation of V is really a rule for e to the V. So it's very natural that the definition of W also should involve only e to the V and not V. Okay? That's one thing it should do, but there are some surprising other things that it has to manage, and it's very hard, if you think about it, to figure out what should happen. For one thing, it has 3 different derivatives, so it's not easy to figure out where to put this e to the V. Besides e to the V, there has to be an e to the minus V. It should have equal amounts of e to the V and e to the minus V, okay? Because then those have to cancel out in some way so that this thing can be gauge covariant. The new W is not going to be gauge invariant, but it at least has to be covariant. But it turns out, in this case for once, I'm sure it can be sort of derived, but there are not many options, and the answer is so beautifully simple that I'll write it for you first. WA, the matrix, which is, this is a spinor index of course, it has an upper index small a, but I'm writing it in its matrix form. So this has no further indices. Turns out to be minus a quarter, d dagger, e to the minus v, d a, e to the v. And the most amazing thing about this expression is that there are no brackets. It's not this times this. Okay, that's not what it is. The way to read this is take e to the v, act with the d, then multiply by this, then act with this, then act with this. Each of them acts with everything on its right. Now, why this peculiar structure? Why in particular did we choose to put it here and not here? Okay. The answer lies in the way this thing transforms under gauge transformations, which as soon as I write it, you will see what's happening. E to the v has to go to e to the minus I lambda dagger, e to the v, e to the I lambda. What do we expect W to do? How do we expect it to transform under gauge transformations? Should not change. The field strength certainly changes in non-abelian gauge theory. Only in abelian gauge theory it's invariant. Yeah, what?
No, not as in.
I'll tell you, in the non-abelian gauge theory without supersymmetry, F mu nu goes to G inverse F mu nu G. Now it's a little embarrassing. In our supersymmetric case, we already used up something like this for e to the v. Okay? It transforms like this, except that wasn't G inverse. That was in the supersymmetric case, it was G dagger, where G was e to the I lambda, X dagger was e to the minus I lambda dagger. This kind of transformation on W would be disastrous. Why?
That would give us a derivative term.
Derivative terms. No, I'm saying if, yeah, that's one reason, that's correct. It would be disastrous because W must transform homogeneously, unlike V which transforms with an inhomogeneous or derivative term. But there's a simpler way to see that this transformation would be a disaster on W. W is a chiral superfield. This kind of transformation doesn't preserve the property of being chiral. Okay, so what we should hope is that W transforms with e to the minus I lambda, e to the I lambda, and W dagger transforms with the other guys. Okay? Well, miracle happens. Let's plug this in here. Okay? So WA equals or goes to after this gauge transformation and with this proposed form of W, it goes to minus a quarter d dagger, and then this transforms by taking the minus sign of everything. So it is e to the minus I lambda, e to the minus b, e to the I lambda, okay, times, I'll continue here, dA times the transform of e to the v, which is e to the minus I lambda dagger, e to the v, e to the I, sorry, thank you, somebody was trying to correct me, that's a dagger, and these are here, this is it. Okay? And again, now this is an expression involving 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, all just written out, and every derivative acts on everything to its right. Okay? Now let's see if we can commute a few things and cancel them off. Well, look at this d. It wants to act on these three terms, but this one is a lambda dagger, so it's an anti-chiral superfield. Even if I expand the exponential, all powers will be anti-chiral, so d will go through them. Okay? Once this comes to the left, it cancels off this one. It's the inverse of this. It's not the dagger of this, it's the inverse of this. Okay? So the lambda daggers have gone. That's a great joy. Lambda daggers have gone from the problem totally after that. Look here, this lambda can go through this dagger and this dagger because it's chiral until it comes to the far left. So this thing, using these two facts, is e to the minus I lambda minus 1/4 d dagger, e to the minus b, d, a, e to the v, and then e to the I lambda. And this is e to the minus I lambda w, a, e to the I lambda. We are done. So you see the wonderful thing about supersymmetry, that while V being a vector superfield was free to transform in a way involving both lambda and lambda dagger, and it does, and also the fact that it transforms like this includes the inhomogeneous term in its transformation law miraculously. In contrast, the gauge field strength superfield W transforms under gauge transformations only by e to the minus I lambda, e to the I lambda, thereby preserving the fact that it's chiral. Okay, and W dagger will transform with the dagger of these, thereby preserving the fact that it's anti-chiral. Very good. So now the only thing left to do to confirm that we've got it right is to expand our W so defined into components in the Wesleyan gauge and see what we get. And after calculation, we find W is equal to, now it's a matrix, it's equal to, first of all, remember that W always started with the gaugino, it still starts with the gaugino, and it still starts with the gaugino. This would be the gaugino if this was the gluon superfield. So lambda, which is a matrix of Y, then there's a D term which is also a matrix times theta A. This is very much the analog of stuff we already found earlier for the Abelian case, but now the fun starts. Here we actually get F mu nu, and in the last place we get theta theta sigma mu T mu lambda dagger. Y. There are some indices, I think this is A, where F mu nu, the matrix, is D mu A mu minus A mu plus IG, which means now we can be quite sure that we did the right thing. Not only did we find a W through this which is gauge covariant in the sense we would expect, but now we've shown explicitly that when we expand it out, besides the Abelian part which we already knew, the non-Abelian parts of it are absolutely as they're supposed to be. And d mu of lambda dagger also should be whatever it's supposed to be, but I might not have written it. but I guess it is d mu of lambda dagger. I'm not sure, plus or minus I g k mu comma lambda. And the important thing here we see is that lambda is also in the adjoint. It's hardly any surprise. Well, I shouldn't say also, it's in the adjoint. Since the natural representation for gauge field strengths is the adjoint representation, which is why in QCD there are 8 gluons, we expect certainly that there should be 8 gluinos in that theory because they will be partners of the 8 gluons, and that means that lambda transforms in the adjoint representation. If you go back to your previous notes, you will see that lambda had no charge in the U1 theory. That's because the adjoint representation in U1 theory is neutral. That's why those fermion, whatever couplings didn't assign any charge to lambda. Okay, and here we see that it comes out in the adjoint representation. So this is all we should expect from our superfield. It should have the covariant field strength for F and the covariant derivative for lambda, and it does. So that's enough for us to be 100% sure that this is right. And finally, it only remains to write an action, but there's hardly anything to worry about anymore. For the gauge invariant action, there's only a new factor, which is that instead of 1 by 4, which was the factor before, we seem to have 1 by 16t of the representation, integral d2 theta, trace of WA plus convex connect. Okay. Since W transforms by e to the minus I lambda and e to the plus I lambda on both sides, the product of two of them does the same thing. When we take the trace, then the e to the I lambda from one side comes to the other side, and it's invariant. The same story goes through in the conjugate term, except that it's d2 theta dagger and W dagger transforms with e to the I lambda dagger. So supersymmetry actually seems to split the gauge transformation in some sense into a holomorphic and anti-holomorphic piece. Okay, because what we saw is that e to the I lambda, where lambda is the gauge transformation superfield, has two natural conjugates, e to the minus I lambda dagger, which is its summation conjugate, and e to the minus I lambda, which is just its inverse, and they are not the same thing. And here we see that the field strength has two pieces, one transforming by e to the minus I lambda, e to the I lambda, and the other by e to the I lambda dagger. And after tracing, of course, both are invariant. The next thing you would do is to generalize the coupling of chiral superfields to these. Well, the chiral superfield should just transform by e to the lambda in its appropriate representation. I don't know if I've written that, but it's pretty obvious. I'll leave it as an exercise for you, what you want to do. The chiral superfield phi has an index I, which goes over the dimension of its representation, and also over any number of copies that there may be. For example, if there are 5 doublets, then I goes from 1 to 2, and there's another index which also keeps track of 5 different doublets. Okay. So this, then e to the v, ij, and then phi j, and there should be a dagger somewhere. So you see, it's hardly very different from the Abelian case. The only thing is we've absorbed that 2g times v a ta, which we find all that as v. And now it's up to you to check that if this, actually there's nothing to check. This transforms on the left by e to the I lambda. This transforms on the right by e to the I lambda dagger. Okay. This transforms on the left by e to the minus I lambda dagger and on the right by e to the I lambda. So it's absolutely obvious why this thing is invariant. For completeness, I'll write it. Phi goes to e to the minus I lambda phi. This is all matrix multiplication. This actually means phi I goes to this ij phi j. Okay. So therefore phi dagger goes to phi dagger times e to the I lambda dagger. And of course e to the v we already know how it goes. It goes as e to the minus I lambda dagger, e to the v, e to the I lambda. So gauge invariance is always right. In a way, it's almost simpler than it is in non-supersymmetric fields, because this had better include all the complicated minimal couplings, capital B mu goes to B mu minus I G A mu whatever. All those things are all built into this, but it's all in factorials. The beautiful part is that there's no derivative to worry about, because somehow the superfield language seems to incorporate differentiation in a natural way. Okay. These transformations actually act on V by terms involving derivative, but the derivative is not manifest. Okay. And the last thing, today for a change I'm actually finishing whatever I set out to do, is to write down and then after this there's also a superpotential term for which I don't have to say anything new. Superpotential is just made up of some gauge invariant combination of the phis, all the phis in the theory. If they transform under non-abelian gauge transformations, then we need to multiply them in the right way to be invariant. And there are no gauge field, there is no vector multiplying involved in that. Okay. So the three terms I wrote at the beginning of this talk all generalize straightforwardly to the non-abelian. One little comment which is very amusing. We didn't say anything about what the gauge group is. We imagine that it might be SU2 or SU3. The interesting thing is that if it is SU2 or SU3 or any SUN, so if the gauge group is SUN, then trace of these generators is 0. Why is that?
Because P is proposing to the combination. PATB is everything.
Okay, that's one way of saying it.
Simple unitary condition.
I mean, it's just the S in SUN. This S condition says that the determinant is 1. If determinant is 1 and the matrix is e to the something, then trace of that thing is has to be 0. Okay. Now, if trace of TA is 0, then it also follows that trace of the D term is 0. So the phi Heliopolis D term that we would have wanted to write down doesn't exist. Okay, because this D is DA, TA. So although there are many auxiliary fields D, there's no D term. Okay, but if the gauge group has U1 factors, so let's take an example. The gauge group is SU3 cross SU2 cross U1 cross U1 cross U1. Perfectly possible gauge group. I'm not saying this is the gauge group, I'm just giving an example. Then there will be a bunch of D, A equals 1 up to 8 for this. Another bunch, I'm not trying to use good notation, you can understand what I mean. Another bunch of DS for this, and then here another bunch of, let's say, D, I don't know what here I'll call it, D I equals 1, 2, 3 for this. So there's one D for each generator. So these are 3 generators, these are 3 more, these are 8 more. There are no D terms for this, no D terms for this, and there's one independent one for each of these 3. So the general D term that we can write is eta I integer di. Okay, I goes from 1 to 3 only for those. Is that point clear? there have to be U1 factors in the theory for us to be able to write a D term. So if we were just making a super generalization of the ordinary standard model, then there will be one D term for the U1 factor and no D term for the other two factors. But in the supersymmetric models, you can have more U1 factors and then each one will have its own D term. And since this is a very simple linear coupling which does affect the dynamics of the theory, we must always include it unless it's forbidden by some other thing like some charge or something. Okay. So what I'll do is I'll conclude by writing super QCD. But we've already seen the important principle before. The important principle is that there will be one non-abelian vector. There will be one vector superfield, this time non-abelian. So B non-abelian, and it will be SU3. It will be an SU3 gauge superfield. So there are 8 components VA. All right. As far as the matter, we have a phi plus, which will have various terms, including root 2 theta q left, the left-handed quarks, and phi minus, which will have this stuff, plus root 2 theta, the left-handed anti-quark. Now I'll put a bar. But the bar, at least in my lecture, bar does not imply any sort of complex conjugation. Okay, because I reserve star for ordinary complex conjugation and dagger if it's a matrix or a spinor. Okay, so it's just a name for the left-handed anti-quark. Okay, and now phi plus, these are matrices, of course, not matrices, sorry, these are actually vectors because these are triplets, these quarks are in the triplet of SU3, so these will have an index I, which will be the SU3 index. And now phi plus under gauge transformations goes to e to the minus 2I G3, the coupling constant of SU3 times TA lambda A times phi plus. Again, this means that this matrix has to be evaluated. Ij indices, this is J, this is I. I think I wrote this once before. Like this. Okay. And phi minus will go by this thing with a plus sign upstairs, but also T A star. If I write phi minus transpose, then it will be phi minus transpose times this on the right side transpose, but star and transpose is dagger and these are Hermitian. So therefore phi minus transpose phi plus is Gaugin as it should be under SU3 gauge transformation. So it's a allowed part of the superpotential. In other words, with this kind of structure we can give quark mass terms, which is just as well. Okay, it's only when the weak interactions enter that will be forbidden quark mass terms because of the difference between left-handed and right-handed quarks. But in pure QCD, you are certainly free to put in mass terms for the quarks. They should be SU3 invariant, and we've seen that they are. So this will be a superpotential, and that's more or less the end of it. Then there will be D terms, and there will be quarks, quark-gluino couplings. Will be. So I'm just choosing a superpotential which only has this, which is only quadratic, so there are no other contributions to the potential, but there will be D-term contributions to the potential. To the potential for phi and phi star. Now what are phi and phi star now? I didn't give them a name, but I should put them in here. They are color triplet scalars, and they are called squarks. They are the super partner of the quarks, occurring in the same superfield as the quark. Since the quark is a color triplet, its super partner must also be a color triplet, so they are color triplet scalars, SU3 triplet scalars. Okay. And those scalars will have a D-term contribution to their potential, as well as quark dash squat dash viewing on couplings. I won't bother to write it, it's all in DGR's book. It's more important that you think where they come from. We've already seen these couplings in the Abelian case. The new thing in the non-Abelian case, in the Abelian case, these were all proportional to electric charges. Now instead of electric charges per se, they are proportional to gauge representations of SU3. Okay. Maybe I could actually do one little thing for you. I could write down the D-term potential so that you will see what I mean. The quarks for gluing are linked to you. So D-term contributions will be, and that is a half G3 squared, this is the coupling constant of SU3, and then summation A equals 1 to 8 in brackets phi plus star TA phi plus minus phi minus star TA phi minus the whole square. Eventually, if we would introduce electric charge into this, then of course these would have charge plus 2/3 and these would have charge minus 2/3. This is all for one quark, so this is like the up quark only. Then if we put in the down, charm, strange and everything, then we usually get the standard model, which is what we'll start from next time. And before I start on this MSSM, I'll also try to spend 5 or 10 minutes talking to you about why we are studying supersymmetric theories at all, something which I didn't do in this course at the end, because these were all preliminaries which I wanted to get out of the way and not yet complete. There won't be any lecture day after tomorrow. I'm afraid I'm going out of town on Wednesday. I'll be back on the weekend. So the next lecture will be next Monday. I'm sorry that this puts us a little behind in the speed at which I'm